Welcome to today's paper reading. Today's paper is titled, Layer-Condensed Kewei Cache for Efficient Inference of Large Language Models. This paper was published on the AR14 preprint by Haoyi Wu and Kewei 2 from Shanghai Tech University. The paper addresses the significant memory consumption issue in deploying high-throughput large language models, LLMs. This issue is exacerbated by the large number of parameters and the substantial memory usage of the key value, Kewei, cache in the attention mechanism of transformer architectures, especially in deep models. To tackle this, the authors propose a novel method that computes and caches the Keweis of only a small number of layers, thereby significantly reducing memory consumption and enhancing inference throughput. Experimental results on large language models demonstrate that this method achieves up to 26 times higher throughput compared to standard transformers, while maintaining competitive performance in language modeling and downstream tasks. Additionally, the method is designed to be compatible with existing transformer memory-saving techniques, allowing for straightforward integration and further improvements in inference efficiency. The implementation code is publicly available on GitHub. The introduction of this paper highlights the significant memory consumption issue of key value, Kewei, caches in large language models, LLMs, which accounts for over 30% of GPU memory. This consumption is directly proportional to both the sequence length and the number of layers, making it a critical bottleneck. Previous research has focused on compressing the Kewei cache to reduce memory usage, such as by shortening the cache sequence or implementing dynamic eviction policies. In contrast, this paper introduces a novel approach that reduces the number of layers, pairing all queries with the keys and values of just the top layer. This method significantly reduces memory consumption without adding computational overhead, inspired by the interpretation of transformer layers as an iterative process of improving token representation. Figure 1 illustrates the difference between a standard transformer decoder and the proposed model. Each node in the figure represents a layer of transformer computation for a single token. The horizontal edge from node A to node B indicates that the queries at node B are paired with the keys and values at node A. In the proposed model, only the keys and values of the top layer are cached, significantly reducing memory consumption. In this section, we discuss the two-layer condensed Kewei cache method, which significantly reduces memory and computation requirements. By pairing the queries of all layers with the key-value pairs, Keweis, of only the top layer, we avoid the need to cache or compute Keweis for lower layers, thereby saving both memory and computational resources. Additionally, this approach also saves model parameters by no longer requiring the weights that map hidden representations to Keweis for these layers. Figure 2 illustrates two equivalent computation graphs for training a model with two layers. Part A shows a sequential training process over n tokens, while Part B demonstrates a parallel training process over n tokens with n iterations. Both methods maintain the same length of the longest dependency chain, ensuring computational equivalence. The parallel approach, however, introduces vertical dependencies instead of horizontal ones, enabling parallel processing. Additionally, gradient stopping techniques are employed to manage memory usage effectively. The authors empirically verify the effectiveness of their method on the Llama model, demonstrating significant memory reduction and throughput improvement. They tested their method with models of 1.1B, 7B, and 30B parameters on NVIDIA GeForce RTX 3090 and A100 GPUs, showing larger batch sizes and higher throughput. For model performance, they pre-trained two 1.1B models from scratch and evaluated them on language modeling and downstream tasks, achieving comparable performance to Tiny Llama while maintaining higher generation throughput. Figure 3 illustrates the mean squared error, MSE, of the key value, Kewei, pairs before and after each iteration. The model is randomly initialized and tested with 2048 tokens. The graph shows that the Kewei values converge rapidly over a few tens of iterations, indicating that fewer iterations are needed to approximate the final Kewei values. This fast convergence is crucial for reducing computational costs during model training. Table 1 presents a comparison of the maximum batch sizes and throughput for standard Llama models and our models on two types of GPUs, the RTX 3090 and the A100. The table highlights the performance with various sequence lengths denoted as x plus y, where x is the prompt length and y is the generation length. The throughput is measured in tokens per second, showing significant improvements in batch sizes and throughput for our models across all settings. Figure 4 illustrates the throughput performance of a 7B Llama model and our model in relation to the batch size on an A100 GPU. Both models are tested with a prompt length and generation length of 2048 tokens. The graph reveals that while throughput increases with batch size up to 32, it plateaus and even decreases at larger batch sizes like 128. This suggests a transition from memory-bound to compute-bound operations, indicating that further throughput improvements may necessitate more efficient computation kernels rather than larger batch sizes. Table 2 presents the zero-shot accuracy of our models on common-sense reasoning tasks. It compares the performance of Tiny Llama, our model with W equals 2, and our model with W equals 10 across tasks like HeliSwag, Abka, Wino Grande, ArcC, Archie, BoolQ, and Pika. The table highlights that our model with W equals 10 maintains nearly the same performance as Tiny Llama, while our model with W equals 2 shows a slight decrease in performance but achieves higher throughput. Table 3 presents the perplexity scores of different models on a 10 million token subset of the Slim Pajama development set. The models evaluated include Tiny Llama, our model with a window size of 2, W equals 2, and our model with a window size of 10, W equals 10. The perplexity values for these models are 9.219, 9.746, and 9.265 respectively, indicating the performance of each model and predicting the next token in the sequence. Figure 5 illustrates the comparison of latency per token and memory consumption between Streaming LLM and our model, W equals 10, integrated with Streaming LLM across various cache sizes. The data reveals that the integrated model achieves lower latency and memory usage, demonstrating its efficiency in handling different cache configurations. Figure 6 compares the performance of Streaming LLM and our model integrated with Streaming LLM in terms of cache size. The evaluation uses 4 initial tokens across all settings and is based on the first text sample from the PG19 dataset. This comparison highlights the effectiveness of integrating our model with Streaming LLM for various cache sizes. Table 4 presents the performance of a model in language modeling with 2 warm-up layers placed at different positions, at the bottom, at the top, and in the default sandwich configuration. The results indicate that the sandwich configuration yields the best performance. This could be attributed to the distinct functionalities of the top and bottom layers, such as semantic processing, which are optimized in the sandwich arrangement. Figure 7 illustrates the language modeling perplexity of our model integrated with Streaming LLM on text containing 4 million tokens. The analysis follows the methodology of Xiao et al., 2024, utilizing the concatenated test set from the PG19 dataset, Ray et al., 2020. The key observation is that the integrated model maintains a stable perplexity, indicating effective processing of the input data. In this section, we empirically analyze the design choices in our method. First, we examine the sandwich configuration of warm-up layers. With 2 warm-up layers, W equals 2, we compare placement at the bottom, top, and in a sandwich configuration. The sandwich style demonstrates the best performance, likely due to the different functionalities of top and bottom layers. Next, we explore the impact of the number of warm-up layers on model performance and throughput. We find that the log dev perplexity does not decrease monotonically with the number of warm-up layers, indicating a trade-off between performance and throughput. Finally, we investigate the convergence of key-value KV pairs. We observe that a trained model requires fewer iterations for KV convergence compared to a random model, and we find that M equals 7 iterations are sufficient for optimal convergence. Figure 8 illustrates the effect of varying the number of warm-up layers on model performance and throughput. The rightmost point, where all layers are warm-up layers, W equals 22, signifies that the model becomes identical to the standard transformer, serving as the baseline. The throughput was measured using an RTX 3090 GPU with a prompt length of 5 and a generation length of 2043. Notably, the log dev perplexity does not consistently decrease with an increasing number of warm-up layers, indicating a trade-off between model performance and throughput. This trade-off can be managed by adjusting the number of warm-up layers, with fewer layers potentially enhancing throughput and more layers improving performance. Figure 9 presents an experiment on a Llama 50M model with different values of M during training. The top part of the figure shows the model's performance with varying M values, while the bottom part displays the mean squared error, MSE, of the key value, KVE, pairs before and after each iteration. The models were tested with 1024 tokens, demonstrating the convergence behavior of the KV pairs during training. In the realm of reducing the KV cache for efficient inference of large language models, LLMs, several approaches have been explored. Jian et al., 2023a, b, focus on compressing document-level prompts into shorter ones to accelerate model inference. Li et al., 2023, aim to remove redundancy in the input context, while Mu et al., 2023, train GIS tokens to replace reusable system prompts. Ren et al., 2023, incrementally compress specified spans of tokens, and Liu et al., 2023, prune unimportant tokens without affecting performance. Ge et al., 2023, propose different KV pruning strategies for different types of attention heads. Zhang et al., 2023, introduce a KV cache eviction policy based on attention scores. Unlike these methods, our approach reduces memory consumption by reducing the number of layers, which can be combined with existing methods for further efficiency improvements. Additionally, feedback transformers, Fan et al., 2020, aggregate hidden representations from all layers, but their sequential training process is time-consuming. Our method supports parallel training, making it more efficient and scalable. Figure 10 illustrates the mean squared error, MSE, of the key value, KV, cache before and after each iteration. The models in question are evaluated using 2048 tokens. This figure highlights how the MSE of the KV cache changes with each iteration, providing insights into the convergence and stability of the KV cache over the training process. In this paper, the authors propose a novel method to reduce memory consumption and improve the throughput of large language models, LLMs, by minimizing the number of layers requiring key and value computations and caching. Empirical results demonstrate significant memory reduction and throughput improvement with minimal performance degradation. The method effectively integrates with other memory-saving techniques such as streaming LLM. Future research will focus on designing more efficient training approaches, developing large batch-friendly kernels, and validating the method on larger and more complex LLMs. However, the method has limitations, including requiring approximately 3 times the pre-training time compared to traditional methods and experiencing throughput degradation with very long prompts. It is particularly suited for tasks with a large generation length, such as translation, dialogue, and question answering. Thank you for watching.